So welcome to Chapter 8. This is going to be about conservation of energy, potential energy curves, that sort of thing. First thing to talk about is some vocabulary. First of all, the datum. We're talking about something having gravitational potential energy. We have to set the height, but we have to set the height from a particular point, and we decide what that is. The datum is sort of the 0 point. If we're above that, then we have positive gravitational potential energy. If we're below that, then we have negative gravitational potential energy. All right. So that's what the datum is. Potential energy comes from objects that are in the system that are going to exert conservative forces. So in this system right now, if I'm going to talk about potential energy, then the objects in the system are the ball and the Earth. If we don't include the Earth in the system, then the force from the Earth is an outside force. And we don't talk about it in terms of potential energy. We talk about it in terms of work done by an external force. So we want to be careful about making sure we understand what's in the system and what's not. Same thing for springs, right? A spring is another source of potential energy. And so if we've got the spring in the system, then we talk about potential energy. If not, we're talking about the work done by the spring as an outside force. All right, so figuring out what's in the system and what's not is important. Conservative forces, this allows conversion from kinetic to potential energy. So Earth is a conservative force, or we could have something from outside, something pushing, and actually if it's outside, then we don't have potential energy. So again, conservative forces are just in the system. Earth is exerting a force, it's in the system, so it converts from potential to kinetic energy. Right, same thing with springs for now. We'll talk about other forms of potential energy, conservative forces in the system. Non-conservative forces are forces like friction in the system. So if this is rolling down a hill and there's friction or a block is sliding, then that would be a dissipative force, something that takes mechanical energy out and it turns into heat in the surfaces of the objects. And then there are also applied forces from the outside. So something like you could have a fan pushing, like a wind tunnel, somebody comes along and pushes something, magnets, whatever it might be, some outside force. And so what we get now is this equation. You guys learned, I think you learned bar charts last year. It's a way of looking at the total energy at the beginning, the work done, and then the total energy at the end. And all we care about are those, the final and initial conditions, and then whatever work is done in the middle. And we're going to see examples of this. This really, the rubber hits the road when we see the examples and you start working through this. But Ki is initial kinetic energy, Ui is initial potential energy, and that can be either gravitational or elastic potential energy. And then we look at the work done by applied forces. So if we've got a wind tunnel, something like that, adding energy, or taking away. If it's taking away, then that's just negative. That W becomes negative. The work done by non-conservative forces, that's the work done by friction, something like that, usually negative, taking energy, mechanical energy out of the system. And then we look at the end, kinetic energy and potential energy again. So here's the problem-solving strategy. Look at the problem and figure out all the forces involved. Do we have Earth? Usually yes. Do we have springs involved? Are there places where there's a wind tunnel, where there's friction, something like that? Split the problem into natural breaks. So look at the beginning, look at the end, and then look at all the things in between. So pick the section where there's the wind tunnel and figure out what that force and the distance is. Where there's friction, figure out what that force and the distance is. And then we put it all together in the equation. And then you're typically solving for something. So again, if we're looking at conservation of mechanical energy, like for example this example with the hill and the roller coaster, the total energy is equal to the total energy at A is equal to the total energy at B equal to the total energy at C. That's the whole idea, that energy is conserved. And if there are no non-conservative forces, if there are no forces from the outside, the total amount of energy just remains the same. Okay, so let's take a look at an example. We have example 1, a simple harmonic oscillator is set into motion on a frictionless surface with an initial velocity of 5 meters per second at its equilibrium. The mass of the oscillator is 2 kilograms. So it's set initially 5 meters per second. At this point, that means it's going to be going this way. It'll slow down and then come back. So it's going to be oscillating like this. And question A asks, what is the kinetic energy at maximum compression? When it's at maximum compression, this is all the way over here. That's where it's actually stopping. So at that point, the kinetic energy is actually 0 joules. All right. B, where is the kinetic energy equal to the potential energy? Okay. So what do I know about this? Well, I don't know what the total, okay. I need to figure out what the total amount of energy is. All right. How do I know that? Well, the total amount of energy is equal to, here at this point, what is the energy that I have? I've got kinetic energy, but I don't have any elastic potential energy because it's at the equilibrium. It's not compressed or stretched at all. So at this point, the kinetic energy here, that's the total energy. So the total energy is equal to the K at 0. And then what I want to know is, where then is the kinetic energy equal to the elastic potential energy? But since K and U are equal to each other at whatever point this is, I'm just going to set K and U equal to each other. Since K equals U, then I can substitute one of these in here. What I'm looking for is position. Right? If I substitute K, then I'm going to find the velocity at that place where these are equal. But instead, I'm going to put U in here. So I'm going to say that K naught, so K at 0, is equal to 2 times UE. All I did was I substituted, since these two things are equal, I substituted this in here. So I've got UE plus UE, and I get that. So K0 equals 2 UE. And what this looks like then, let me go up here, a little more space. So this is 1/2 mv squared plus, or not plus, equals 2 times, and then the elastic potential energy is 1/2 kx squared. I know m, I know v, right, at position 0, and I know what k is, so now I just have to solve for x. So this cancels out with that. I'm going to divide k over to this side, so I'm going to have m v naught squared over 2k equals x squared. So x, this position, is m v naught squared over 2k, and I take the square root. Simplify a little bit more, v naught root m over 2k. So this is 5 meters per second. The mass is 2 kilograms, and 2 times, and this is 20,000, and I don't have the actual number, so I don't know what that is. But whatever you get here, you'll end up with plus or minus some position. Again, this is the important part anyway, setting it up. Right? And so what we're saying is, at that point, that's the place where the kinetic energy and the elastic potential energy are the same. Right? And then part C, what is the maximum displacement of the oscillator? Let's go back now and look at gap C and see how this works. All right. Let's look at the whole equation. Okay, I'm comparing two places. This is where I have my information, so I can use this as my initial point, versus the place where it has maximum displacement, whatever this is. This, let's just call it x. All right, maximum, does it say compression? Just says maximum displacement, so that's here or over there. This is my final condition. So in the initial condition, when it's here, I have kinetic energy. There's no elastic potential energy. Is there any work done by any outside forces? What's the system here? The system is the block and the spring. That's it. No work is done by any outside forces, so this is 0. It says we're on a frictionless surface, so there's no work done by non-conservative forces. At this point, this is the place where it's stopping briefly, like we saw in Part A. So Part A is helping lead to this. That's where the kinetic energy is 0, so that's 0. So now I take what I have from this equation and I put it in. So kinetic energy, 1/2 mv squared equals 1/2 kx squared. Right. Similar to what we had before, but how is it different? Well, I don't have a 2 in here. I'm not adding this up twice. Instead, what we're saying is all of this energy now is in the form of elastic potential energy. And now I'm just going to solve for x. So it works same way, and here what we actually end up with is 5 times 10 to the negative 2 meters. When you do the algebra and you solve for x, you should get that, which is really 5 centimeters. You can give your answer either way. Let's take a quick look at the graph. What would the graph look like for this? Let's graph the total energy, the elastic potential energy, and the kinetic energy. A is amplitude, by the way. So if this thing is oscillating back and forth here, what's happening to the, let's look at the this energy, the elastic potential energy. Well, at 0, the elastic potential energy is 0. And at the amplitude, that's where all of the energy is in the form of elastic potential energy. And at maximum compression, that, again, when it's at that negative amplitude, that's where all of the energy is in the form of elastic potential energy. So this looks like this. So elastic potential energy versus displacement looks like this. What about then the kinetic energy? Let's use a different color. Kinetic energy is 0 at the maximum amplitudes, but it's at its highest point at 0. So that then looks like this. So the orange here is kinetic energy. The blue is elastic potential energy. And this dotted black line is the total energy. So what we're looking at here now is we've got a box, spring, it's a frictionless surface, so the box is here where there's no stretch in the spring. So it's at its natural length, and then we let it go. So the box comes down and then stops at some point. So we want to know how far along the incline did the box slide. So we've got this distance here, x, however far the box slides. The force on this, so we want to know, at first it's got a certain amount of gravitational potential energy, and then there's work done on this. So the amount of gravitational potential energy is mg. Now we've got to be careful. It's not x, right? Because instead what it is, it's going to be this distance right here, this vertical distance that it's going to fall down. But we want to do this in terms of x because x is how much the spring stretches. Right? So mg, and this is going to be x sine of theta, this distance right here. Right? If we do a little bit of trigonometry, if this is the distance x, this is 40 degrees, and so this distance is x sine 40. Right? So that's the amount of gravitational potential energy it goes through. So what am I doing? I'm setting my datum here at that bottom point. Datum. The starting position is up here somewhere. Okay, and I can move the datum wherever I want, so I can do that. This is the amount of gravitational potential energy that's used up in it falling from here to here. That then converts to elastic potential energy. At the end, what I have is, now this spring is stretched. When I first release it, it's not moving, so kinetic energy is 0. When it gets down to the bottom, it reaches a point where there's no movement, so there's no kinetic energy there. There are no outside forces, there's no work done by friction. So all I have is gravitational potential energy at the beginning and elastic potential energy at the end, so this is 1/2 kx squared. All right, I'll cancel out an x, make it a little bit easier. What do we want to know? How far down the incline did the box slide? So we're looking for x here. So this is going to be 2 mg sine theta over k. That's what x is equal to. And so we get 2, the mass is 2, g, we're just going to use 10 sine of 40, and k is 200 Newton meters. That should come out to about 12.9 centimeters. That's how far it goes. The second question now is, what is the acceleration of the box at that instant? All right. So we're just going back to Newton's second law here. F net force equals ma. What are all the forces on the box at this point? All right. Well, one is the force due to gravity, and it's pulling down that way. And we'll say that we want to make that negative or positive. We'll make this negative. Plus the force from the spring, that's going to equal ma. So the force due to gravity is mg sine theta. So negative mg sine theta. Plus the force due to the spring, which is going to be kx, equals ma. Right. So when you plug these numbers in, x is the stretch in the spring, so we get negative 2 times 10 times sine of 40 plus k, which is 200, times x, which is 0.129, divided by, again, 2, which is the mass. That should give you an acceleration of about 6.4 meters per second squared. Right? And that, since I made this is the negative direction down, this force is positive pulling up, so my acceleration is in the same direction as that force up. Because what's happening? This box is coming to a stop and then changing direction and going back up that way. Example 3. Find the distance traveled by the block before it comes to rest. So at the beginning, this has some kinetic energy. It has gravitational potential energy. And then, is any work done by an outside force? No, because it's box and earth. Those are in the system. I've got gravitational potential energy. Is there any work done by a non-conservative force? Yes. Right now it's going to hit the friction there. And so the work done by friction is going to be negative because it's going to be taking mechanical energy out of the system. So this is going to be mg times mu. So this is the force of friction times the distance, which is given to me as d. And then at the end, I have 0 energy. No kinetic energy, it's come to a stop. 0 potential energy because it's at our datum level. And that's it. So now all I'm doing is I'm solving for d. Right? I want to know what is d in this case. So I've got negative mu mgd equals negative 1/2 mv squared plus mgh, or rather minus mgh. So then I'm solving for d, so this is going to be 1/2 mv squared plus mgh over mg. That's it. Just leave it like that. We don't even have to plug in any numbers. Okay. And we can cancel out m, simplify this a little bit so it looks a little neater. 1/2 v squared plus gh over mu g. Interesting to notice then that the distance this goes is independent of the mass. Okay, example 4. So here we're finding the distance traveled by the block in the area where there is friction before it momentarily comes to rest. All right, so there's this, oftentimes in a test or some type of problem set, there'll be something like this to indicate that there's friction along here. So this block is coming this way. That's a force. So we draw the arrow over here. So this is V1 going that way. And there's no friction here, but once it hits here, there's going to be some friction. And it's saying that it's going to momentarily come to rest. So initially it has kinetic energy, so 1/2 mv1 squared. Nothing else at this point. That's all the energy it has. It doesn't have any elastic energy. It doesn't have any gravitational potential energy. But then once it hits here, what this is saying is that there's going to be some friction exerting a non-conservative force. So this is going to be negative mu mg, and I'll just call this x. I'm calling this x because however far this goes, that's also the compression of the spring. That's the key to this problem, recognizing that this, how far this goes, is the same as the compression of the spring. So that's going to be 1/2 kx squared. All right. And then however far it compresses, that's the place where it comes to rest, so there's no kinetic energy at that point. So all I have on this side is elastic potential energy. And I don't have any numbers, so all I'm doing is I'm solving for x. That's all I'm looking for? Yeah, just the distance traveled. So, since I'm solving for x, I have x squared and I have x. This is going to be a quadratic equation, right? Sorry. So I've got negative 1/2 kx squared minus mu mgx plus 1/2 mv1 squared equals 0. And now I apply the quadratic equation. And so this comes out to x equals negative mu mg plus and minus square root of mu mg squared plus 4 negative 1/2 k. This should be minus, but then it'll be plus with that. Times 1/2 mv squared. That's positive though, so I leave that. All over 2a. So this is going to be 2 times 1/2 k. And we can simplify this a little bit, right? Multiply the 4 into here. So the 4 and the halves go away. This becomes positive. This just becomes k. Once you simplify it, then that's your answer.